Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
He was the co-chair of a new workshop on the abstract interpretation of object-oriented languages, which I found to be quite interesting, and I hope that workshop will continue in future years for some of us to submit papers to as well. He's going to tell us about his thesis work and about how to deal with object-oriented programs. So welcome.
Okay. Thank you, Ruslan. Thank you for inviting me there today. So the talk of today is about object-oriented languages and the static analysis of object-oriented languages. In particular, the goal for the analysis we want to present today is to have a static analysis that enables to analyze object-oriented programs. In that, it handles the features of object-oriented programs as inheritance, encapsulation, and polymorphism. That allows to analyze classes in isolation. In that, we don't want to make any hypothesis on the instantiation context. That is a composition in that we can reuse the result of the analysis in order to analyze larger programs, and that relies just on the program, on the source code, and not on annotation, if possible. And furthermore, we wanted such analysis to be sound, in that no behavior is ignored. In particular, the analysis we present is able to infer class invariants. Class invariants are properties that are valid for each instance of a class, for each instantiation context, and before and after the execution of any public method of the class from the context. As an example, we can consider this class stack. So what we want is to have an analysis. So we have a stack. It has three fields. That is a size of the stack, a position to the first empty element in the array stack in which the elements of the stack are contained. So what we want is to infer properties like this. For example, that the pointer to the head of the stack is always positive and at most equal to the size of the stack. Then the size of the stack is always at least equal to 1, and that the size of the stack does not change during the object lifetime. We also want to infer class invariants for subclasses in a modular way, in that if we consider, for example, this extension to the class stack with the other two elements in order to perform an undo, what we want is to infer some properties on undo and properties about the position of the head of the stack depending on the value of undo. We want to infer such properties without accessing to the source code of the base class, but just to its invariant. Finally, such properties can be used, for example, to prove that at this point the stack is not empty, so that this can be used for verification and optimization. The analysis we present is based on abstract interpretation, that is a general theory of approximation, and formalize that the semantic of a language can be more or less precise depending on the observation level in which we put ourselves. Sorry. A static analysis is an abstract semantics that is precise enough to capture properties of interest and coarse enough to be computable. Furthermore, it's automatic and it covers all the possible executions. As the outline of the work is like this. We start with a core object-oriented language, then we introduce aliasing, inheritance, and finally we see how to improve the result of the analysis considering the context. Finally, we have the conclusion, the future work. In this minimal object-oriented language we start with, we assume no inheritance, no recursive classes, and in particular, we assume that for each method, the type of the input values and the type of the return values is of basic type, so that actually we have no reference types for the parameters or result. We drop this hypothesis later. Yes? That I cannot have something as a method, for example, in which I have a method of a class B in which inside this method I have A, I have some variable type A, and then I have another class A, which in your method I have some variable type B, so that I have A and B, something like this. Actually, we can do it, but for simplicity, it's better not to do at this point. So this is a small example. This class is such a class has two fields, A and B, that are initialized by the constructor, and then we have two methods that increments one variable and decrements the other in a dual way. As an example of the semantics we're going to use though, for instantiation, we consider one particular instantiation of such a class with the 4, 5, and then we have at the beginning, after the execution of the constructor, we have a state where A takes 4 and B takes 1. Then we can execute either the context can invoke either the method add, either the method sub, so to have 3, 2, and 5, 0 here. And then we can go on in such a way so that we have all this trace there. And intuitively, we have an invariant. This is that the value of A plus B is always equal to 5. That actually was the value it was passed as actual value for the parameter C of the constructor. We formalize, in order to formalize such intuition, we start by considering an abstract model for an object-oriented language where a class is modelized by a triple made by a constructor, a set of variables, and a set of function definitions. And in particular, we made the assumption, just to simplify the exposition, that all the fields are protected. The states then are just a function from variables to values. And the semantics of method and constructor just consider, for example, that of the constructor consider an input value and returns a set of states, so to model non-determinism. The semantic on object is then modeled as a partial trace semantics in which each trace represents an evolution history of the object, in which the first state is the state of the object just after the creation. And all the other states are the result of interaction between the context and the object. So we do in general, so we consider a set of initial states. We consider the collecting semantic on methods, that actually is the lifting to set of states of the semantics of a method, and then we consider the transition function here that actually invokes given a state all the possible methods starting from this state. Then the semantics of a class can be given a fixed point form as follows. So we have this fixed point in which we start with initial states, then we consider one trace in the set of trace, and we consider the last state, we apply the transition function, and we have this trace here. So such a class is the strongest class property, in that it describes a behavior of a class in all the possible contexts. However, we are interested in class invariants, so we want to perform some abstraction in order to retain just the states, and so to abstract away the history of computation. We formalize it as Galois connection. So we consider an abstraction function that collects just the states in traces, as we see there, and actually forgets the trace structure of the consequences between states. With such a definition, we can rewrite a fixed point of before for states in this form. And such fixed point is sound, and the best way to illustrate such a fixed point is the following picture that gives you an idea of what's going on for computing class invariants. So we have the constructor, we have the states that came after the execution of the constructor that participate to the class invariant. Then such states are pushed at the beginning of the methods. Methods are executed starting from the states, and then the results of the execution are all collected together. The result of this collection is pushed back to class invariant, and then we have all this process here of iteration that brings to a fixed point. And then the fixed point is a class invariant.
For invariant, you mean something semantic, right? Set of traces?
Yes. Here the invariant actually is a set of states.
Set of states.
Set of states. That's the idea.
Semantical object.
Semantical object, of course. Yes, it's something that is inferred from the program, and is something that is valid here just before executing. Once we get a fixed point, it's valid here before the execution methods, and here after the execution methods. Actually, by sounds is also true here and here. In the running example, we have that we can compute such an invariant by fixed point computation, starting from the empty set. The first iteration, we have the state that is given after the execution of the constructor. Second iteration, we have the states that came from the execution of the method add and the execution of the method sub. Third iteration, we have two further states, and so on. After omega steps, we reach a fixed point in which we have these infinite sets of states, and we have the property that x plus y, where x and y are the values of a and b, is equal to 5. What we want to do is to compute it automatically, and actually this method is not effective for two reasons. The first one is that we need omega steps, so we cannot do it on a computer. And the second one is that the size of these sets can be infinite, so that we cannot represent it on a computer. So that's in order to overcome to this problem, what we do is to perform an abstraction, and in particular we interest on properties of interest. We assume a Galois connection that approximates set of states, and we assume an overapproximation for the initial states of the class and overapproximation for the semantics of the methods. Then we can rewrite the equation before, the fixed point equation before, for the state-based class invariants by substituting for the union of sets the join of the abstract domains. For the semantics, the corresponding abstract semantics. And we have a nice theorem that says that what we do here is sound. In the drawing, actually nothing changes except that here we have a join operator in the abstract, and somehow here when we do with this fixed point computation, we need to perform a widening so to assure the convergence of the iterations. For the example we've seen before, what we do is to instantiate the abstract domain with the domain of linear equalities that dates back to Karen 76. The idea of this domain is to have elements that keeps equalities among linear equalities among the variables of a program. Then we have that the order is subspace inclusion, the join is subspace union, and other things. And this domain respects the ascending chain condition so that we do not need widening in order to ensure the termination. We perform the iteration. So we start with the bottom of the abstract domain. Then at the first step, we have the abstract execution of the constructor. To the second step, we have the abstract execution of the two methods, add and sub, starting from the state just after the invocation of the constructor that gives these two properties. And once we perform the union of subspace, we obtain such a property. With a further iteration, we'll see that S3 is equal to S2, so that we have effectively reached the fixed point, so that what we obtain is a class invariant. In particular, we obtain that the value of A plus B is always equal to C, where C is the value passed to the parameter of the constructor. What we want to do now is to extend this framework with aliasing. And in particular, we consider the case in which the types of the parameters of the methods and the return value belongs to reference types. What we obtain as a consequence is that the object may expose each state to the context. So we have to see how to deal with it.
Question.
Yes?
Before you go to aliasing, even if you work with basic types,
Yes.
the linear equations can take you only so far.
So far, what do you mean?
Not very far.
Not very far?
Because it's linear equations. Even if you have something algebraic,
Yeah.
quadratic, the linear equations will not capture it.
Oh, it actually depends on the property you are interested to prove.
Of course, yeah.
That's the point. So you have actually a series of abstract domains that capture different properties. So for example, you have linear equalities, this one, but then you have congruencies. To capture congruencies, you have a polyhedra in order to obtain do a kind of a convex Euler of the values, so that can be useful for approximating.
A library of such things.
Yeah, there are several libraries for such things, and also, if you want something very strange, there are also some abstract domain for ellipse that can approximate the values taken by variables by one ellipse, and they are useful, for example, in the analysis of floating point computations. I hope it answers your question.
Yeah.
So we have to Aliasing, and we have to this C++ class in which we have two fields. We have one constructor, something that performs a step. The idea of this class is it performs a kind of random walk, depending on the value of the Boolean there. And we have one method that returns a reference to the Boolean, so that actually the invocation of this method causes the address of goWrite to be exposed to the context. As a consequence, we have that, that's not right, we have that when the context invokes getDir, then it can obtain a pointer to the internal state of the object, and so the context can modify such an object, such a value in an arbitrary way. So what we have to do is to, in the concrete semantics, to handle this case, and then to show how to handle it in the abstract. Essentially, in the concrete semantics, the difference with the reference what we have done before is to add a further transition it is in order to consider when the context change the value of one address, the store location that corresponds to an address that has been exposed by the object. So we consider the memory, we see the memory divided in an environment and a store. An environment is a map from variable to addresses, and the store is a map from addresses to value. Then the semantics of constructor and methods is modified accordingly, so considering store environment here. And what is interesting is that when the addresses are contained in values, then the object may expose a part of its state. In order to capture this exposition from the part of the object of its state, we consider something, we create something, we define something that we call interaction states that intuitively encode the result of interaction between a state, a context, and an object. In particular, an interaction state has an environment and a store that are the environment and the store just after the interaction. A value is the value that is, for example, given by the return value from a method. And this is more interesting, is a set of addresses that are all the addresses that have been exposed by the object so far until this point. So, for example, the initial states of an object O are given by the execution of the constructor with some values. And we have that the execution of the constructor, for simplicity, do not return any value, and hence it does not expose any value to the context. More interesting is the situation for methods. For methods, we use at first one auxiliary function reachable that intuitively captures all the memory addresses that escaped in a given configuration of the store, starting from a given address. And the collecting semantic method does like this. I'll take a set of interaction states, then I take one of these, I'll take one input value, I execute the method with this input value, the environment and the store given by the interaction state. I obtain a new value, a new environment, a new store. So the value goes there, the environment and the store goes there. And then from the value and the new store, I consider all the addresses that have been exposed by this invocation of the method M. So I update the set of addresses exposed so far. And these addresses, I remember there. Then what it does, what we call the direct interaction, is just to give an interaction state to consider all the possible invocation of all the possible methods from this state. The second form of interaction is the direct and indirect interaction in which the context arbitrarily change one value of addresses that have been exposed. So we have an auxiliary function update that changes one value that given an address, and the store change arbitrarily the value of the address. And then what it does, the context, is just to take an interaction state, to take an address from the interaction state, and to change it arbitrarily. And this gives rise to a transition function for the indirect interaction. Sorry. Then the fixed point partial trace we have seen before can be expressed in such a form in which the transition now are two kinds, one direct that we have seen before and one indirect that we introduced right now. We perform the abstraction of two reachable states, and in the fixed point equation now we have a new component, that is this context, that stands for the behavior of the context on the exposed addresses. And intuitively, such a context stands for a malicious context that changes the values of all the addresses that have been exposed so far. In the example, we start always with the empty set as a beginning. Then a first iteration, we have the execution of the constructor. So the state is a little bit more complex right now because you have the environment, the store, and so no value is returned and no address is exposed. In the second step, we have, starting from this step, either the execution of the method to do a step, so they change the values to 4, either the execution of the method that exposes the part of the state. So it returns a value B. A value B actually is a memory address. And we remember in this component here that we exposed B. And this empty set came from the fact that at the beginning context, there is no address that has been exposed, so context is just empty. Second step, we have some part of this S3 that came from a consequence from this state. And what is more interesting is this one, in which we start from a context in which we apply context to this state. So context knows that B has been exposed, and then it changes arbitrarily B to true and false. So we consider the two cases. We consider, in order to have something that is computable, so in order to have a static analysis for that, we consider an abstract domain that approximates a set of interaction states as before. And the new thing now is that we have this further approximation of the context. This gives rise to a fixed point characterization in the abstract of the context. And what is interesting is that the soundness hypothesis we have seen in the slide before implies that the abstract domain, the underlying abstract domain that we use for the analysis must be powerful enough to capture escape information. In that, it must be the analysis actually must contain at least escape analysis in order to capture, in order to be able to see which addresses are exposed by the execution of one method. And as for context, it's very easy to implement it because actually it's just something that takes a set of addresses and it put them to top. It is the worst case assumption in abstract interpretation. As for the example, we consider an abstract domain now is a little bit different. We try to use linear congruencies. Linear congruencies is an abstract domain introduced by Granger in the 90s, and they capture information of this type on values of variables. So we have linear congruencies to approximate the value taken by the pos field. We have bool, that is the lattice of booleans, in order to approximate the value taken by the variable, the boolean variable inside the object. And then we have this two that actually says which field escapes. We perform the iteration, so we start from the bottom. At the beginning, after the execution of the constructor in the abstract, we have that the value of pos is equal to 0, that the boolean is true, and that no field has been exposed. In the second step, we have that the situation that came before, we have the one that came from the execution in the abstract. do step method. So we have that pos is equal to 4. We have the one that is given by the execution of the get dir method, so that expose go right. And the third one is that the context in the abstract is bottom. We perform the union in the abstract of the tree, and we obtain that pos is a multiple of 4. Then the Boolean is true, and then one field may be exposed to the context. Then we go on with another iteration, and now we have that what interesting is the contribution of context that sets the value of the Boolean field to top. It is I don't know, and so doing the union we obtain this stuff. We can go on with iteration until we reach a fixed point, and essentially with this fixed point what you obtain is that the value pos is always an even number, the value of the Boolean field it's unknown, and the class may expose a part of its state to the context. In particular, is the field go right. So far, we have seen the parameter. You have seen the return values. Actually, we can also handle the parameters on non-reference type, and I'll go quickly on that actually. So if you want, we can talk offline. And the idea is that when we have a parameter of a class B that is different of the class we are analyzing now, what we want to do is to use the invariant we have already computed. Or another thing we can do is to assume the worst case top. On the other hand, when the parameter of the class is of a type that is the same type of the class we are analyzing, what we do is to introduce this point in the fixed point computation. So this second case is illustrated by this example. So we have that we are analyzing the class head, and we have that head is here. Then at the beginning we have that val is equal to 5. Then we increment val by accessing to the value passed there. What we do there is a series of fixed point equations where at the beginning we have that after the execution val is equal to 5. Here we use the abstract domain of intervals, in which the value of one variable is approximated by an interval of all the possible values it can take. So we have a value at the beginning is equal to 5. And the second step, what we do is when we analyze this method, is to pass the approximation we have so far of head, so that a dot val is equal to 5 as input there. So what we obtain is that val is 5 plus 1, then 6. So when we go there, we have that either val is 6, either is 5. So it is between 5 and 6. And so it is what says this interval there. Then we go on, and we have that val is equal to is between 5 and 7, and so on. So this iteration do not stabilize, and so we need of a widening operator so to reach a fixed point. And so we can approximate by saying that the val is between 5 and plus infinity, so that is always greater than 5. Question?
On the previous slide, what if you repeated that if-do step as we did, took two such steps, saying self.val gets a.val plus 1,
Yeah.
and then self.val gets maybe self.val minus a.val.
Okay, so you say there? I had something there?
But so my question is, if you had such a second assignment there, what would your analysis think that a.val could be? The same as on entry, or is it affected by the assignment to self.val?
Okay, you say if you have some assignment to a.val before?
No.
Okay.
So this assigns to self.val.
Yes.
But of course, if self
okay. See your point. No, it always assumes that it is equal to the first iteration before. Okay. Yes, because if not, it's true that you can also have the case where you have something as a.val equal to something else. And that's a problem, because here you violate the property. So what I do in this case, if I have a.val equal to something, is to assume top, because at this point I violated the invariant. And for me, here is not in the definition I use. invariant must not hold here. So if it is not modified, it's okay. If not, I cannot say. Any other question?
Suppose it says a.val plus 1.
Yes.
Unless the value reached 100, and then you don't increase.
Okay.
So 100 is a big number. So in your fixed point computation, you may jump to infinity before.
You have something else in abstract interpretation, which is called the narrowing, and helps to reach this, to solve this problem, more or less, or to help to solve this problem. So the idea is you do fixed point computation. So at a certain point with my widening, I go there. So that is between 5 and plus infinity. So I've done very high in the lattice. And then what I do is I apply this narrowing. It's a kind of dual of widening that helps me to find actually have the condition it is more than 100. So there is something like this. It does not work all the times, but yeah. Okay. So far, we have presented an abstract interpretation that obtains a sound approximation of the class semantics, in which the class invariance is automatically derived from the class source, and it is parameterized by the underlying abstract domain. But we did not consider inheritance so far. So let us consider this extension to the classes that we have seen before. We have a new field. We have a constructor that invokes the class constructor, and then it set the value of the new field C to this C0. And we have a new method that decrements the value C and the value of A. What we want to do is to analyze this class somehow. The first immediate solution, at least is the solution that I know is the most used in in analysis for object-oriented languages that exists so far, is to expand the subclass relation. So the idea is just to do some syntactic transformation. So to copy, it's a little bit more complicated, but the idea is more or less like this, is to copy the methods that came from the superclass and to copy the fields that came from the superclass, and then to resolve somehow the invocation to super, to this, and something like that. So what we can do, one way to apply what you are saying so far, to analyze inheritance, is to do like this. We expand inheritance, and then, expand inheritance, and then we apply the fixed point computation we've seen before to the expanded class, so that we have some methods that came from the base class and some methods that came from the extension. And in the case we've seen before, we can do it, and we can obtain such an invariant. Here again, we use a different abstract domain. This is the one of linear polyhedra, or of linear inequalities, called also polyhedra. And so we can obtain this invariant by doing the fixed point iteration we've seen before. The problem with this approach, there are several drawbacks, about it, is that the expansion of inheritance may cause a quadratic blow up of the code source, because we have to expand for each class in the class hierarchy. Then we have also that a base class for different subclasses must be analyzed several times. That is, each time that we have if one class has several subclasses, we need to expand all the subclasses and then to analyze each of them, so that actually we do not share the computation for the analysis of the base class. And the third problem, or maybe less important, is that the code of B may not be available, or at least in the form that we are in the source code we are considering in the analysis. Our goal is to obtain a class invariant for a subclass without accessing to the source code of the base, but just using its invariant. And so what we want to do is just to have such an invariant, and we compute it by looking at invariants that have a particular shape, in which we have two components. Intuitively, we have two components in which one comes from the extension and the other comes from the base class. In order to do it, we consider for simplicity, we consider three orthogonal aspects. That is class extension, then methods redefinition, and polymorphism. So how we deal with the class extension? The idea is that when we have a just class extension, when we have subclassing, and so we add new methods, what we are doing, we are adding some behavior to these classes. And the idea is that the class we obtain, the subclass, may behave either as the base class, so when we invoke one of the methods of the base class, either as the subclass. So this is intuitively. And this either, this or, we can formalize as this join in the abstract domain. And what we want to do is to have, so the invariant, it is the invariant we've seen before for the base class. And the other invariant that just considers what is new in the extension. So that we have a constructor, and this is a constructor of the extension. We have the methods that are just the methods that are provided in the extension of the class. And the invariant we pass there that is actually considered also the one that we already know that is of the parent class. This is fine under some assumption. In fact, there is a theorem. This theorem it says that under this some assumption, this is sound. It's good to do it. And the assumption is that the subclass invariant do not violate the subclass. The constructor of the subclass do not violate the invariant of the constructor of the superclass. And the second one is that the abstract semantics we are using is a joint morphism, not necessarily a morphism. Then, under this hypothesis, we have that looking for an invariant in such a way. So I recall.
What does it mean, joint morphism?
Joint morphism, it means that f, you have a function f, so you have that f of a join b is equal to f of a join f of b.
Morphism respects.
With respect to join. Okay, yes. And but it's just for join. I do not need to be complete for. Okay.
That's also just continuity, right?
Continue.
That's stronger.
Stronger. I think
property.
Because you want it over into the chains. This is just over two.
I think continue. You have a chain.
Yeah, that's
chain.
true.
But here I just
Distributes or disjunctions is what it means.
Right.
And okay. So under this assumption, we have that. The invariant construct like this. So one component from the base class and one component from the extension is really an invariant if and only if this condition on the methods of the base class is respected. The problem with this condition is that in general it can be very difficult to verify such a condition. It can be computationally equivalent to analyze the expanded class. So we have some other theorems that says that under some assumption this theorem is holds, so that we can do it. And in particular we have that this is the case, this is true, if the subclass preserves the invariant of the superclass. Or this is also true if the static analysis we are using, the abstract domain we are using is an abstract domain that is called to be relational, that can keep relational information in a symbolic way between the parameters of a method, so that we can approximate, for example, one method with a relation, a symbolic relation that relates the parameter of the method and the output value of the parameter. This is the case for most of the abstract domain of numerical abstract domain that are used in practice. So we are lucky, we are very happy about this. In the example we have seen before, we have that, so we use linear inequalities, so that the hypotheses of the theorem are satisfied. So we can consider a base class invariant that we computed before. Then we can compute with a fixed point computation, always in the same way, an invariant just for the extension, this one, and then we can perform the join between the two in order to obtain an upper approximation to the invariant of the expanded class. It is worth noting that such an approximation, such an invariant is an over approximation of the invariant we would have obtained in the direct way, because in the direct way we remember we obtain that A plus B is equal to C. Here we obtain something that is weaker, that is A plus B is smaller than C0, and C0 is smaller than C. So we lose some information, actually. And the intuition about it is that when we look at this form of class invariant, what we have to is that the component, the part that comes from the base class is fixed. And so the information comes from the base class to the extension, and it does not propagate on the other way around. It's for this that we have some loose information. And we consider a little bit quickly because I think I'm running out of time and I want to do something interesting. So we have method redefinition here. We have the problem is that when I redefine a method, I can have down calls and up calls. And the down calls are when a method from the base class calls one of the extension, and one of the extension calls one of the base class. Then in this very small example, we can see that if n belongs to the base, if m belongs to the base class and n belongs to the subclass, then this invocation calls the invocation of one method that belongs to the extension. And when I'm writing, I'm analyzing the base class, I do not know nothing about the subclasses. So in order to analyze it in a sound way, the only thing I can do sound is to assume the worst case. To assume the worst case at this point here, just after the invocation, because I can always write a subclass that changes the state of the object in any way. The dual expect is when m belongs to the extension and n belongs to b. So that in this case, I have an up call, and here I can do something better because I can analyze the methods of the superclass by assuming the top, and so I can use here something better than the worst case. Nevertheless, without no annotation, we cannot hope to do something better. But in the case we've seen before, we can obtain something good. For example, we have the stack as base class. We obtain the invariant. Then, in the extension, where we have some invocation to the methods of we have some up calls in the example. Here not up call and up call. Using what I said before and using the domain of polyhedra and the refinement of the execution with trace partitioning, we can obtain a significant invariant in which we have that the invariant of the parent is false, the value of undo is between -1 and 1, and then depending on the value of undo, the position to head of the stack may change. This point is about polymorphism, and is always with an example. It is an extension of stack. Then we consider an extension of stack in which the post stack is an extension where push is redefined so to always push a positive number in the stack. The point is how we can prove this function to be correct. How? Because this function performs a square root of an integer, and in this case, intuitively, it holds because as post stack is always positive. Then, when you do the square root of a positive number, we do not throw a mathematical exception. But this is not assured for all the subclasses of post stack. So the idea is to define some notion of a behavioral subtyping based on a static analysis on what we said before. And I go fast on that. Is not so interesting, at least. And so what we want to do is like this: is to notice. The idea is we have to remark that a class invariant as computed so far is a behavioral type of the class because it describes the behavior of the class given the property of interest we are in. Then we can say that a class A is a behavioral subclass of B if the class A preserves the invariant of B. And this preserves, in abstract interpretation terms, can be given as it is something that is lower in the abstract domain we are considering. And so, question? Okay. So if we have A and B, two classes, we can consider the static analysis as described so far. And then we say that if the class A preserves the invariant of B, then we say that is a behavioral type, a behavioral subtype of this one. And this notion allows for the verification of a polymorphic code as we have seen before, because for the class post-stack, we can use the abstract domain of signs that gives the sign of one variable. And using that, we can show that all the entries in the array are positive. And in particular, as they are all positive, when we perform a pop of one element, then it is positive. Then, if all the classes that are in the system are and that are subclasses of poststack are behavioral subclass of poststack, then by soundness this is true for all the subclasses. And so this is one way of doing. Yes?
Do you have to infer somewhere that pop actually returns something from the stack? I mean, it seems like the thing you've inferred so far is just that things in the stack.
Yes.
But you need to link that to the return value from pop, otherwise a subclass could come along and just return. It doesn't ever put anything negative in the stack, it just happens to return negative numbers from pop.
Okay, I see what you want to see.
But I didn't see where you're able to infer those between return values.
Yes, I think you do not really need to do it, because what you are interested in is that it returns some value. So, do we have a definition for pop? I do have no definition for pop, I'm sorry. The idea is that what you do is you smash in order to obtain this property. Okay, entering stacks is ending arrays is very difficult in static analysis. So one thing you can do is to smash all the values in a stack with the one integer, with the one signs that approximate the signs of all the elements of the array. Then you have that this is positive. When you do the fixed point computation, you have that it's positive. Then you have that this stack here, this array is all positive. Then you do a further step, and you see that you have a positive. You take some element from an array where everything is positive, so the return value is positive. I don't know.
I understand that. I just don't see where in your invariant it's talking about the state of the object, but this is the property of the return value of a method in the class.
Oh, okay. Sorry, I have no slide here. So you are saying I'll infer this one. I do not need actually to say that it came from the stack because I have the code.
But not
so I'm interested in the value, not in from where it came. But you say where I have for this definition here. What I want is that the value returned by pop, actually, this one, I cheated. This one is not defined just in terms of class invariant. It's a term of class invariant, a post condition of methods. I cheated, so it's for this.
So do you have an effective way to actually verify this type behavioral relation?
Yes, that's nice. It's because as this object here is defined in terms of disorder. Disorder here is the order on the abstract domain. By decidability of static analysis, disorder must be decidable. So it's a relation that is decidable. So actually, how it is defined, this stuff, I say that this one is smaller than this one if the class invariant here is smaller with this object, with this order, or this one. And then for each method post condition. And actually, I have method post condition because if you remember the drawing before, when I do the union, actually, before doing the union, I have a post condition. I can show that it's a post condition. The union is just the approximation of all the post conditions, so to have the invariant. So it's just, I have it for free. And yes?
Okay, so that makes sense. So, but in your example before, where you showed how to positionally compute the subclass invariant, we actually obtain a less precise invariant than the base class has.
Yes, that's
so this would not work in this.
It does not work.
Okay.
It does not work.
I just wanted to...
The two are orthogonal, yes. The first work fine. This one implies the second one because if I have something that is a behavior subtyping, so I'm happy because the theorem I said before it holds. So actually the union, I have no need for union because do something here. If it preserves the invariant, then it is something that is smaller than the invariant. Then it is the invariant itself. So I'm done. So behavioral implies this one. I'm happy when I have behavior subtyping. This one, by the way, works in all the cases that are interesting. I don't know if it's clear. So the last step is about context approximation. It is useful for the analysis of mutual recursive classes. And what we want to do is to improve, because right now we are seeing an analysis that consider all the possible context. Now we want to see if it's possible to improve the analysis when we have some hypothesis about the context. In particular, we have the code that contains the context that instantiates some object of some class. In this example, we have some code that instantiates an instance of S. Then you do a push and non-deterministically perform either an undo, either a pop. So we know something about the context. Can we improve the results so to prove that, for example, here we have no underflow or overflow? And furthermore, what we want is to split the analysis in two, so to have analysis of a context and an object in separation, so that this enables a form of audio analysis and of parallelizing the nice two. And we start from an assumption is that we have some object-oriented code that is made as a context and an object, and we have some semantics for this that takes as input some initial state, abstract initial state, and it returns some abstract value. And what we want to do is to take this C and this O and to analyze the two in separation. The idea for doing it is to approximate the behavior between the interaction between the context and the object with a regular expression. And intuitively, we have a regular expression in which the atoms are object like this, in which we have a set of methods that are the methods that can be called at a certain point from the context, methods of the object that can be called from the context. We have some input value, it is an approximation of the value that are passed, and some approximation of the memory configuration. So for example, a context that creates an object and then it calls any method of the object is done like this. So it creates an object, it calls the constructor with any value, any context, and then it calls any of the methods unbounded number, a specified number of times. So it's possible to split semantics. I do not give the details here because I'm really running out of time. It's possible to split such a function once it is formalized into. In the first one, it is one analysis that take one context and one approximation of the object, and it returns one value and a regular expression that approximates the behavior of the context on the object. And the second one is a function that takes an object and it takes a regular expression that somehow specifies which methods are called in this object, and it returns an approximation of the semantic of this object under this context. If we consider the two functions, we see that the function for the context takes as input an approximation of the object that is the result of this function. And the approximation for the object takes a regular expression as input that is returned by the approximation of the context. So we have a mutual recursion here. One way to handle it is by using a greatest fixed point computation. And so we start by assuming for the analysis of the object an unknown context, so as we have done so far. And for the context, an unknown object. So we start with the top of the two. And then we have a greatest fixed point computation that starts from above and goes down. And the nice things about this is that each step of the iteration is a sound approximation of the semantics, so that we can stop iteration as soon as we have proved the property of interest. So, for example, in this code, we infer this regular expression that says that before first thing we call push, then either we call undo, either pop, and then we call push, and we can use it to prove this one. Or more interesting, we consider this class. This class is a kind of writing of the class we have seen before, the class sys we started with, and it has some y that is incremented or decremented, so that actually we can say anything about y when we compute the class invariant for C. And we consider this code in which we create two instances of a class C. Then we do some fixed point computation, some iteration with some properties to check here. And in one case, we call the methods for A and B of the object O1. In the other case, we call 2 times the method A of O2. And what we want to prove is that this property holds here. And the property is a property about the fields of the two objects. So to prove this, we use the abstract domain of polyhedra, and we start by computing the class invariance for the object. As I said before, the class invariant does not say anything about y, so that actually we can, when looking at this property, a class invariant just talk about this part here of the property, this part here of the property, but does not say anything about y, so that we cannot prove this property at the first step. So what we do is to analyze main using replacing the object with the invariant we have computed. And okay, what is interesting are the regular expression we obtain now, and is that for the first object we call the constructor, then we call get y, and then we call get y add and add b, and unbound a number of times, and the same for R2. And using these two regular expression, we can push this to the semantic of the object, so to obtain the semantic of the object under the context that is approximated by such regular expressions. And now we obtain some property about y. So in particular, that y in the first case between 0 and 1, and in the second case it's always positive. As a consequence, we can show that p is verified, because now as it is always positive, we knew that this is equal to 0. This is always positive, so all p is greater than 0. So p is verified, so we are happy, we can stop the iteration, and the thing is that the result we obtain is not the most precise one, but we are happy because we proved the property, so we can stop. And for example, if we do another iteration, we can prove that there's branch is never taken, but it was out of the interest of the property. So we can stop iteration as soon as we want. The advantages of doing this is that the analysis can be parallelized, because now we can analyze the context, the object on two different machines, for example. So we can reduce the overall cost of the analysis, so that actually we can use more precise domains to analyze the two components. Then we have that each step of the greatest fixed point computation is a sound approximation of the least fixed point computation, so that we can add the iterations as soon as we have get the desired precision level. And finally, we can it's easy to see how we can modify this schema in order to handle multiple recursive classes, so that we can approximate the interaction between these two mutual recursive classes by two regular expressions. So we have the conclusions, and we have presented a framework for the static analysis of modular analysis, for static analysis of object-oriented languages that try to endorse and to exploit the main features of object-oriented languages, particularly encapsulation, inheritance, and polymorphism. And the framework we presented can be sketched, summarized as a framework that has 3 axes of for tuning the analysis. One that is the abstract domain. So we have a generic abstract domain or a symbolic relational one if we want to analyze, for example, subclasses. Inheritance can be handled either direct or either in a direct way, either using the modular analysis we've seen before. And the context can be approximated either by worst case, so a context that can do anything, or we can use regular expression to approximate it. For the future work, we want to extend some analyzer that we have for a subset of Java. Then we want also to extend the theory in order to infer invariants, temporal invariants, that is somehow say something about the evolution history of a state. And then all this stuff can also be used for giving a semantic characterization of class hierarchy, and then of manipulation of class hierarchies. And so this enables for a formalization of refactoring, class merging, and other stuff. And that's all. Yes?
I have a question. I never saw you make any assumptions about if you have a class with fields that are of reference type to,
Yes.
that is, to other objects. Do you assume that they're encapsulated within this class, that is, that they're not used for reference from other places?
Okay, in that case, I do like this. I can statically see if, for example, suppose that it's a field of reference type, is okay? Okay, not a variable in the middle, okay. In this case, what I do is like this. I can run, is the hypothesis on the soundness that gives rise to escape analysis. So I can use escape analysis to see if this reference type, this reference field, is being exposed to the context.
Or comes in from outside?
If it comes from outside, then what? You say if I assign something.
For example, in the constructor or some other method.
In this case, either I use the invariant of the reference time that I pass. I assume for the field that I have, I put the reference, the invariant I already have. Or I have a kind of mutual, either I have one class that depends on the other, and so I can use the invariant. Either I have that also this class depends from the other. And so either I analyze the two together, so I have a big fixed point for the two. Either I split the two using the context approximation. Or either I have a third possibility that you stop. I assume top, but that's the worst possibility that I prefer not to use. So it's
you
a way.
can treat them independently.
Yes, I can treat it in three ways. And so the idea, theoretically, what one wants is to have an analyzer that allows you to tune the precision and the speed.
How do you find actually the right domains? Because your program doesn't say anything that you should use linear equalities or polyhedra or whatsoever.
You have to go to Paris and study there.
Yes, it's, you have some heuristic for some property of interest and something like this. The idea is that more or less there are some kind of properties you want to verify. For example, the beginning of this study, actually, because it's just my PhD thesis, so I can say it's not so old. What I'm interested in is improving the absence of runtime exceptions. So something you can do is to use all these numerical abstract domains, so to see that one array is not accessed in a wrong position or things like this. And so actually the abstract domain, so the property you obtain, you want to infer, depends on the property you want to prove. So the idea is you have a large literature on abstract domains, and then you choose the one you prefer, and you implement it, or you use the library if it already exists.
Sorry, following up on that, if you didn't care about the expense, couldn't you simply run all the domains you know about simultaneously, and the ones that go to top, just throw them away, ignore them?
Oh, yes, you can do it, but actually you have also another issue in doing like this, is that, okay, you have to program all the abstract domain, because the one that exists, and some are implemented in C++, some are implemented in OCaml, and something like this. So once you are writing your analyzer, you choose one language, then if you want to reuse it. So you have this practical problem. The other one is that actually abstract domain is just one part of the game. It's because when you perform abstract interpretation, you have two kinds of loss of information. One that is a static one is choosing the abstract domain. Another one that is dynamic, that is, for example, the widening was the question before. So even if you run the abstract domain, a very precise one, it gives stop. Maybe it gives stop because of the widening. So so you have also this problem.
Right. So you would almost need a kind of engine where the domains could negotiate with one another. So one of them would say, I would like to widen now, please. And the other, you know,
yes.
It would be very complicated.
Yes, you can have this. I know.
It would be sort of akin to building a theorem prover with multiple decision procedures that all collaborate with one another, sharing information, all that kind of thing. I mean, it would be a complicated architecture that way.
Yes, you can have something like this. So another solution can also be, given the same abstract domain, running at a certain point when you need to do a widening, then you can fork and then said, okay, here I run the widening, here I wait other 2 or 3 iterations, here I wait other 10 iterations, something like this. That also can be maybe easier as architecture to do that. That's some kind of heuristic, and then it depends on what you want to prove, actually.
Sounds like going to Paris is easier.
I do have another question. Dealing with references and pointers, a lot of abstract interpretation work that's been done in that space has been centered around shape analysis. Would you find shape analysis a useful addition to what you're doing, or does it not matter, or is it not relevant, or could you plug in, or what's the relation?
Okay, I think I can plug in. I think it's good if I want to prove some properties, for example, about data structures. Something would be interesting. You have a class that implements one list, then you want to prove that actually it implements one in a cyclic list. So you can use one shape analysis. So that's, yes, interesting for proving some properties. It's true that right now I'm interested more on runtime errors, so I'm not looking shapes. What I'm interested in is just, for the moment, is aliasing, is just to have sound approximation, so to have a sound analysis, so that it takes care of aliasing. And what I really need for all this analysis about aliasing, so you can see you have shape analysis, you have pointer analysis, you have escape analysis, and something like this. What I really need is escape analysis. It says that this this reference is not exposed, it does not escape. Yes, but it will be very interesting actually to prove other things, but I'm alone.
So Francesco is going to be here the rest of the week. So I'm setting up some one-on-ones, and if I missed you, or if you really want to take your first pick at the time, then let me know. So thanks very much again.